Welcome to this session. Today we are going to discuss the continuation of last session concepts only, the basic concepts of graphs that we are going to concentrate. Now, some of the definitions. What is a complete graph? So here, a simple graph of order n is greater than or equals to 2, in which there is an edge between every pair of vertices, is called a complete graph. It is also known as a full graph. So that means if you are going to consider any pair of vertices, there is a dedicated edge. There is a dedicated edge to that pair of vertices. Such a graph is there, then that graph is known as a complete graph. In other words, a complete graph is a simple graph in which every pair of distinct vertices are adjacent. Now, a complete graph with n is greater than or equals to 2 vertices, which is going to denoted as Kn. It is nothing but a complete graph with n vertices. Complete graph, let us consider, we are going to consider some of the complete graphs of vertices 2, 3, 4, 5 vertices. We are going to discuss. Let us go to how a graph is like this. This is, we are going to connect. This is V1 and this is V2. So, this is a complete graph with 2 vertices. This is K2. And if I am going to consider another graph, let us say I am going to take another graph is like this. So, which is a 3 vertices, let us say V1, V2 and V3. Then we are going to consider this as a complete graph with 3 vertices. Any pair if you are going to consider, V1, V2 if I am taking, one edge will be there. Or V1, V3 if I am considering, one edge is there. V2, V3 if I am considering, one edge is there. So, this is a complete graph with 3 vertices. And similarly, we are going to consider the complete graph with 4 vertices. Let us, I am taking, this is one vertex, this is another vertex, this is another vertex. Let us, we are going to consider like this. So, between these two, one edge, between these two, one edge. So, here I am taking, this is V1, this is V2, this is V3, this is V4. So, for each and every pair of vertices, there is an edge. So, this we are considering it as a complete graph with 4 vertices. Similarly, if I am going to consider, let us take 5 vertices. So, this is, now this is V1, V2, V3, V4, V5. So, let us, I am going to consider V1. So, I am just taking V1, V2, V3, V4, V5. So, V1 to V5, I am connected one edge. V1 to V2, connected another edge. V1 to V4, another edge. V1 to V3 is another edge. So, V1 to the remaining all vertices, R1, vertex 1 to remaining all vertices, there are edges. Similarly, V5 to V2, V5 to V3, V5 to V4, V5 to V1 is already there. Then V4 to V1 is there, V5 is there, V2 will be there, I am just connecting. Next V3 will be there, just I am connecting. Now V3 to V2 will be, and the remaining already having the edges. So this is a complete graph with 5 vertices. Complete graph with 5 vertices. So this complete graph with 5 vertices is known as Kuratowski's first graph. This is known as a Kuratowski's first graph. So we are considering it as Kuratowski's first graph. This graph is known as. Now, bipartite graph, another definition. Bipartite graph is, let us suppose a simple graph is there is such that the vertex set V is the union of two mutually non-empty sets V1 and V2 such that every edge in G joins a vertex in V1 and a vertex in V2 is called a bipartite graph. And if the E is the edge of this graph, then the graph is denoted by V1, V2 and edge set E. So here V1 and V2 are called bipartite of the vertex V. So that means any vertex set, let us say vertex is V, and vertex set is partitioned into two vertices, V1 and V2, non-empty vertices, V1 and V2. See here, and here partitioned means V1 union V2 should be equal to V, and V1 intersection V2 is equals to empty. That means that there is no common element in this. So they are designed. So here V1 and V2 are called bipartites or partitions of the set V. So, and that graph is denoted by like this. Let us consider, we are going to take one example of the bipartite graph. I am going to take, let us A and B and C is V1. That is, V1 is consisting three vertices and V2 is consisting, let us consider PQRS here, ABC and PQRS. This I am considering in a V1 set, this is in V2 set. Now this I am going to take it as P and vertex P and the next vertex Q and vertex R and vertex S. So now this vertex set can be partitioned into this. I am going to write V1 union V2, whereas V1 intersection V2 is equals to, see here, V1 and V2. They are designed. Then now the thing is, I am going to connect AP. Edges set are A to P. Let us say connecting this A to P, then A to Q, then another one A to R, then another one is B to R. So this is B to R. Then another one is C to Q. Then another one is C to S. So these are the edges. Now here every edge in G join a vertex in V1 and a vertex in V2. See, whatever the edges if I am considering, let us say E1. E1 is connecting A and P. E2 is connecting A and Q. E3 is connecting A and R. Like that it will be moving. That means every edge in G is joining one vertex in V1. Let us, I am just taking, this is in V1. Then I am considering this as in V2. This I am taking it to V2. So every edge if I am considering, it is going to join one vertex in V1 and one vertex in V2. And G contains no edge that joins two vertices, both of which are in V1 or V2. That means there is no edge will be there connecting the vertices of V1 alone or connecting the vertices of V2 alone. See here, there is no edge between AB or AC or BC or whatever the vertices will be there. There is no edge. Here also in the same thing, whatever the vertices are there in V2, there is no edge connecting these vertices. So here, this is going to here, the bipartite is V1 is one bipartite and V2 is another bipartite. Or we are calling it as a partitions. So here a graph is said to be a bipartite graph. Then the vertex set is partitioned into two sets and then there is an edge will be there in the graph that should be from one vertex of V1 to another vertex of V2, and there should not be any edge between the vertices of V1 and between the vertices of V2. Such a graph is known as a bipartite. So we are calling it as G is the bipartite graph. G is the bipartite graph. Let us consider, I am taking another example. So here I am just taking PQRS. Let us take PQRS. So here I am just connecting a simple graph like this. So here vertex set is nothing but just we are taking it as PQRS. So here if I am taking V1 as P comma S and V2 as Q comma R. In this way if I am going to consider, then V1 union V2 is equals to V, and V1 intersection V2 is equals to null set, and there is no edge from P to S or S to P. There is no edge from Q to R or S to P. So I can say that this graph is Z2. This I am going to write V1 comma V2, then the edge set, and whatever the edge set will be there. So that I am going to consider this as this is the graph. So here edge set is a PQ and QR, QS and SR and PR is the edge set. Now this graph is known as a bipartite graph. Bipartite graph if you are going to partition in this way. Suppose if I am going to consider another graph, let us we are going to take like this. Just we are going to consider another graph is like this. So here if I am going to take P, Q, R, S. So here this is not a bipartite graph in any order that you are going to partition the vertex set. Partition the vertex set in the same earlier whatever the way that we are going to partition. Then here P to S, here P to S, there is an edge. There is an edge. So this is not a bipartite graph. This is not a bipartite graph. So whereas this is a bipartite graph. And let us consider another one is, just I am going to consider another problem. I am going to take a device. This is, I am just considering a graph which is of this form. So I am just taking A, B, C, then P, Q, R. If I am going to consider in this order, then A, B, C and P, Q, R. So here the vertex set is V equals to what is given A, B, C, P, Q, R is the vertex set. Then I am going to partition in this way. V1 is V1 as then A, B, then C, and V2 as then I am going to consider P, Q, R. P, Q, R. In this way if I am considering, then V is partitioned into two sets, and at the same time there is no edge from A to B or A to C or next B to C and next P to Q and Q to R and R to S. So in any vertices if I am taking from V1 and V2, there is no edge. There is no edge. So we can say that this is also a bipartite graph. This is also a bipartite graph. So here we are just giving some of the graphs. G2 is a bipartite, G3 is not bipartite, whereas Z4 it is a bipartite. It is a bipartite graph. Now we are going to say the another definition is what is a complete bipartite graph? What is a complete bipartite graph? So complete bipartite graph. A bipartite graph is called complete bipartite graph when we say that whatever the bipartite graph is given, which is said to be complete bipartite graph, if there is an edge between every vertex in V1 and every vertex in V2. Every vertex in V1 to every vertex in V2. See the above diagram Z. G is not a complete bipartite graph, because every vertex in V1 to every vertex in V2 there are edges. So here A to S there is no edge, and here B to P there is no edge, B to Q there is no edge, and C to R there is no edge, and C to R, C to P there is no edge. So this is not a complete bipartite graph, not a complete bipartite graph. So let us consider, I am just taking the complete bipartite graph. We are going to define it as K comma R, K of R comma S. That means R is nothing but the number of vertices in V1 and S is nothing but the number of vertices in V2. Then here R is less than or equal to S, R is less than or equals to S, and so that is going to be defined as a complete bipartite graph is K of number of elements in V1, comma number of elements in V2. Then the R plus S vertices, this is nothing but the total number of vertices in the graph will be R plus S, and the total number of edges will be RS. So that we are going to consider the size and the order. Order is the number of vertices, that is nothing but R plus S, and size is R into S. Let us consider, we are taking some examples of a complete bipartite graph. So here just we are taking, let us, I am going to consider one. I am just taking one graph is like this. I am taking A, B, C, and of course P. So this I am going to consider V1 is only one element, and V2 is three elements, A, B, C. Now the thing is, from P2 there is an edge for A and for B and for C. From here edge, and from here edge. So we can say that this is a complete bipartite graph, and V1 is having one vertex and V2 is having three vertices. So we are going to denote this as K of 1, 3. Suppose if I am going to consider the another one is, let us, I am just taking, so here I am just considering another example is, let us take like this. So here A, B, C, D, E, and here it is, let us say P. Once again I am taking V1 as P and V2 as A, B, C, D, E. So from P to A there is an edge, P to B there is an edge, P to C there is an edge, P to E there is an edge, P to D and P to E there are edges. So we can say that it is a complete bipartite graph and it is denoted as K1, 5. K1, 5. What is this order? What is the order of this graph is 6. It is nothing but 1 plus 5. There are 6 vertices are there. So the order of the graph is the number of vertices in that. So here the number of vertices are 4. The order of this graph is 4. And what is that size of the graph is 3. And what is the size of this graph is 5. Size of the graph is nothing but the number of edges which are there in that. So which is going to be defined with this R into S. So based on that, so here 1, 2, 3, 4, 5. So the size of this graph is just we are taking it as 5. And now let us consider this is I am taking vertex is V1 is only one element. Let us go for, I am taking the vertex set V1 as, I am just taking another example like this. See here A, B, then it is P, Q and R. So from A to all vertices of V2, that is P, Q, R, and similarly from B to P, B to Q, and B to R. See here, V1 as, we are taking it as A, comma P, and V2 as, this is a P, Q, R. P, Q, R, the other vertex. So, what is the total vertex V is A, comma, B, comma, P, comma, Q, comma, R. Now here, there are edges like A to P, A to Q, and A to R. Similarly, B to P, B to Q, and B to R. So here, this is a complete bipartite graph, which is having vertex of V1 is having 2 elements, and vertex of V2 is having 3 elements. So this is the other complete bipartite graph. Now I am going to take one more. So let us consider. So 3 and 6 vertices. I am going to take 6 vertices. So this is A, and next B, and next C. Then this is P, Q, R. Vertices are now A to P, and A to Q, and A to R. There are edges. And from similarly B to P and Q, and next R. And similarly C to P, then it is Q, then it is R. So here V1 I am taking it as A, comma, B, comma, C. And V2 we are considering it as P, Q, R. Then how it is a bipartite, complete bipartite? A to P, A to Q, A to R. Similarly, B to P, B to Q, B to R. And C to P, C to Q, and C to R. There are edges. So we can say that this is a complete bipartite graph. So that is going to be denoted as K33, which is known as Kuratowski's second graph. Kuratowski's second graph. What is this? Order of this graph is 3 plus 3. That is a 6. That is a 6. The order of this graph is 6, and the size of this graph is 3 into 3. 3 into 3. That is 9. So the size of this graph is 9. So in this way, we have just identified. We are going to know what is the difference between a bipartite and a complete bipartite graph. So complete bipartite, a very complete bipartite graph is nothing but a bipartite graph, but converse need not be true. Now let us go for the similar things. How many vertices and edges? How many edges are there in complete graph of K of 4, 7 and K of 7, 11? And next another one is, if the graph is R, K of R plus 2 has 72 edges, then what is R? So here K 4, 7 if I am considering, so it is a complete bipartite graph. V1 is having 4 vertices and V2 is having 7 vertices. Now the thing is, how many vertices and how many edges are there? So the vertices are just, we are going to add the suffixes. So 11 vertices it is having. Then the edges are 4 into 7. So it is 28. It is a 28. Similarly for K 7, 11. So number of vertices are, total number of vertices, which is equals to 7 plus 11 is 18. And the total number of edges, which is equals to 7 into 11, which is 77. And this is for A. And B, if I am considering, if the graph K of R plus 2 has 72 edges. So K R, 2, K R, 12. So how many edges it is having? So the edges are 12 into R. So which is given already? 72. So R is equals to 72 by 12. So there are 6. R value is equals to 6 whenever K R, 12 is having 72 edges. 72 edges. Now here, some of the simple problems will be there. We are going to draw a graph, we have draw a diagram of a graph in each of the following. So here it is given, the first one is vertex set is given. So vertex set is, let us say, I am just taking in any order. So I am just taking A, B, then it is C, and then it is D. The first one is 4 vertices it is having. So A, B, C, D. Now edges, if I am considering A, B, this is A, B, then A, C, then A, D, then C, D, then C, D. So this is A, D and C, D. So how many edges are there? 1, 2, 3, 4. 1, 2, 3, 4. So this is for first one. And the second one is we are going to construct the graphs for the given vertices and edges. Now the second one is there are 5 vertices will be there. Let us we are going to consider V1, then it is V2, then it is V3, and then it is V4, and then it is V5. There are 5 vertices. Now edges are V1 to V2, V1 to V2, there is first edge, V1 to V3, V1 to V3, then V2 to V3, V2 to V3, then V4 to V5, V4 to V5. So this is another graph. So this is the first problem graph, this is the second one. Now the third one is, so here it is having 5 vertices. So P, Q, R, S, T. So we are just considering the 5 vertices are P, in any order you can consider, Q, P, Q, R, S, T. Let us take, in any order you can consider S and T, in any order. So there are 6 vertices. Now P to S, then Q to R, this is, then Q to S, this is the third graph. And the fourth graph, if we are considering the fourth graph, so there are 6 vertices will be there. So what are that? V1, then it is V2, then V3, then V4, then V5, then V6. 6 vertices. Now the edges V1 to V4, V1 to V6, V1 to V6, V1 to V6, V4 to V6, V4 to V6, V3 to V2, V3 to V2, then V3 to V5, V3 to V5, then V2 to V5, V2 to V5. So this is the other graph. So there are just a simple vertices and edges will be there. Then how to construct a graph, and if we are going to represent in a different way, we are going to consider the vertices in different ways, we are going to get the shape is different, the graph shape is different, but the number of vertices and the number of edges will be the remain same. Now here one of the simple problem is given. Let us PQRST. R represents 5 cricket teams. Suppose that the teams PQR have played with each other and the teams PST have played with each other. So now we are going to represent this situation in a graphical notation, and we have to determine the teams have not played with each other and the number of games played by each team, So for this, we have to consider the 5 cricket teams as 5 vertices. 5 cricket teams we are considering as 5 vertices. So let us say how many cricket teams there will be? 5 cricket teams. So we have to consider PQ, then R, let us say, and another one is S, and another one is T. Consider the 5 cricket teams as 5 vertices. That means each vertex represents one cricket team. And whenever there is edge indicates if there is a match between those two teams, then we will represent one edge. Edge indicates if there is a match. So here PQR have played one game with each other. So P to Q, in between them there is one match. So edge will be there is one match. One match between P and Q. One match between P and R. One match between Q and R. Q and R. Now, PST, if I am considering the second one, it is given, PST have played one match each other. So, PT they played one match, PS they played one match, and TS they played one match. So, this is whatever they are given. We are constructing, we are taking that conditions into the consideration, and we are going to construct a graph. So by taking vertices as cricket teams and edges as whenever they are having the match, then edge represents there is a match. So E1 edge, let us say E1 edge is there from P to Q, then it indicates there is a match from between P and Q. So here E2 will be there, similarly Q to R, and E3 will be there, similarly P to R. Now the thing is, the teams, hence determine the teams that have not played with each other. Not played with each other. Not played with each other means whenever there is no edge, between any vertices, then there should not be any match. So first one is the teams have not played. Have not played means there is no edge between R and S, and no edge between R and S. And the next one is no edge between T and R, no edge between S and R, no edge between T and Q, no edge between S and Q, like that. See here, S and Q there is no edge, S and R there is no edge, R and T there is no edge, R and T there is no edge, S and R there is no edge, and R and S same, S and R is also S and Q, and T and Q, then the remaining is T and Q. So this is not there, it's already mentioned. So 4 teams have not played with each other. Then here the second one is the number of games played by each team. The number of games played by each team. So A that is nothing but the degree of that vertex. So here A is played how many A, the number of games A played by, so here A played 4 matches. Okay. How many games are played by each of the team? So P to Q is 1 match, P to R is 1 match, and P to S is 1 match, and P to T is 1 match. And next Q to another one is, so how A is played 4 matches. And what about P is played, P played 4 matches. So with whom it is played? P to Q will play, and P to R will play, and P to S is played, and P to T is played. Then Q is how many matches it is played. So it is played with P and next R, paired with P and R. And similarly T is nothing but P and next S. And similarly S is with only P. So if you want to find out the total number of games that they are played means number of edges. So here 1, 2, 3, 1, 2, 3, 4, 5, 6. So they played 6 matches. Okay. So each team means, so P is played 4 matches. Q is played only 2 matches. T is played only 2 matches. S is played only S is played with T also. P as well as T, like that you can determine that. So the total matches are nothing but the number of edges. Like that you can solve this type of problems. Now, here what is a regular graph? So here, a graph is said to be, this is a regular graph. A graph in which all the vertices which are having the same degree, that means the k degree will be there. Then we can say that it is a regular graph of degree k, or it is a k regular graph, Suppose if I am going to consider, I'm just taking, so here we are going to consider this is this graph. This graph, each and every vertex is 2. I can say that it is a 2 regular graph. Suppose if I am going to consider in this order, let us say I am just taking in this order. What is each and every vertex degree is? This is 3, this is 3, this is 3, this is 3. So I can call it as 3 regular. Suppose if I am going to consider, so some of the 3 regular graphs will be there. So here particular regular graphs are the cubic graphs will be there, and next 2 regular and 4 regular graphs also will be mentioned in that way. So here 4 regular. Suppose if I am going to say that what is the Petersons graph, if I am taking, let us say the Peterson graph is, we are going to consider. So let us take the graph which is of this form. So I am just taking, then it is like this, and then I am just taking. So here it will be. Then if I am considering this type of a graph, so what is here? Each and every vertex is degree is only 3. Degree only is 3. So such type of graphs, this is we know this is a Peterson's graph. It is known as a Peterson graph, which is having 10 vertices and 15 edges. And similarly we can construct the 4 regular graphs also. Like that. See, the regular graph is nothing but each and every vertex degree is the same, whatever it is. If it is a 2, then we can say that it is a 2 regular graph. If it is a 3, we can say that it is a 3 regular graph. And if it is a 4, we can say that it is a 4 regular graph. But this is not a complete graph. Okay. Even some of the things, see here, why it is not a complete graph? Because there is no dedicated edge will be there from one vertex to remaining all other vertices. So that is the difference between a regular graph. Regular graph, if I am considering a complete graph with 5 vertices, and each and every vertex degree is, if I am going to consider a complete graph with 5 vertices, let us say I am just taking like this. So it is a complete graph with 5 vertices. What is the degree of each and every vertex? Degree is 4. I can say that it is a 4 regular. I can say that it is a 4 regular. But a complete graph will become 4 regular. That means all complete graphs, if I am taking, so earlier whatever we discussed, so let us say I am taking this is a complete graph with 3 vertices. So what is each and every vertex degree is 2. So it is known as a 2 regular graph. So all complete graphs with n vertices is known as n minus 1 regular graphs. But all regular graphs, that means a complete graph will become a regular graph, but regular graph need not be a complete graph. So that is the difference between these two. So here it is only a 3 regular graph, but it is not a complete graph. It is not a complete graph. If you observe this, it is a 2 regular graph. It is a 2 regular graph. It is not a complete graph. It is not a complete graph. It is not a complete graph. If I am considering this, so here you observe this. So this is a 3 regular graph and it is a complete graph. It is a complete graph. So from this, and there are edges. So, and here also there are edges, and here also there are edges. So that is the difference between a regular graph and then a complete graph. Now let us we just considering one more in any. Suppose we are just considering, it's not handshaking, I am just leaving this. So one of the prove that one small problem. Let us say example. Prove that the number of edges in a simple graph, number of edges in a simple graph of order, so which is greater than or equals to 2, cannot exceed n into n minus 1 by 2 edges. n into n minus 1 edges. So that means in any simple graph, if you are going to consider, then the maximum number of edges are n into n minus 1 by 2. Let us, I am going to consider G is a simple graph. That means it is having, let us say, n number of vertices. It is having n number of vertices. So of course, the edges, if I am going to, that means in a simple graph, there should not be any multiple edges. So if edge will be there, that should be one pair of vertices. So here n vertices are there. That means in a simple graph, the number of edges cannot exceed the number of pairs of vertices. So here the number of pairs can be chosen. Can be chosen in from n vertices is nc2, which is nothing but n factorial by n minus 2 factorial into 2 factorial. This is n into n minus 1 into n minus 2 factorial by n minus 2 factorial into 2 factorial. These two get cancelled. So it is 1 by 2 n into n minus 1. So these are the maximum number of edges. Each pair can be represented by selecting the edges. It is nothing but the edges. It is nothing but the edges. So the maximum number of edges in any simple graph, is n into n minus 1 by 2. n into n minus 1 by 2. Suppose if I am going to consider, let us say, if I am going to consider a simple graph of order, simple graph of order 4, then how many edges it is having? So order 4 is nothing but number of vertices in that simple graph is 4. Then how many maximum number of edges are? 1 by 2 into n is nothing but 4, and the next one is 4 minus 1. So this is nothing but it is a 6. So if you are going to consider any simple graph of order 4, then how many maximum number of edges are? Only 6. Like that we can calculate. Whatever the n value is, just we are going to substitute in this, and we are going to find out the maximum number whenever the simple graph is having. So with this, I'm going to conclude this, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.